Hey, welcome back to Math with Patrick. Today is November 8th, and we're solving problem 312 from the Daily Epsilon calendar. And the answer is supposed to be 8 because that's today's date. We just need to find the number of regions in a Venn diagram with 3 intersecting sets. Well, let's just do it quickly, and then let's talk about it a bit more. A triple Venn diagram basically just needs 3 overlapping circles, and then it's also important to put a box around it just to show what your universe is or what everything could possibly be. Because it's totally fine if in your triple Venn diagram that something just isn't in any of your 3 sets, right? Like if we have, say, students in a math class, students in a biology class, and then students in an English class, well, a student doesn't have to take any of those classes. So if our universe, say, is like high school students, then it's totally fine to not be in any of those 3 categories. Then we could, of course, have the 3 categories that have just one of those classes, just math, just biology, just English. What did I say? And then we could also have those 3 categories of taking 2 classes, but not all 3. I just skipped the number 6. And then finally, we do have this 8th category of taking all 3 classes. And that's it. That's the whole problem. But I do kind of want to talk about how to generalize this to other Venn diagrams, maybe with 2 intersecting sets or 4 or 5 intersecting sets. Because, maybe if we're thinking in this scheme of like high school classes, why should I only stop at 3 intersecting sets? Maybe let's do like 20, right? Because there's feasibly 20 or more subjects that you could take in high school. So let's think about maybe one intersecting set. It doesn't really intersect anymore, right? Either you are in the group or not in the group. And I'm actually going to make maybe a vector to show this, where basically we could put a 0 here to indicate that we're not in the group, or a 1 to indicate that we are. And there are 2 options out of basically a 0 or a 1. And it would make sense that we then have 2 options to either be in the group or out of the group. And I'll just put a little 0 here to indicate maybe this little vector here would have the information of not being in our set. Here, if we have 2 intersecting sets, then we're going to have 1, 2, 3, 4 different places we could be. And then maybe a vector that looks like this would encode the information of yes being in the first set, but no not being in the second set. And so ultimately, I think this information would probably plunk us in this spot right here, assuming that this is our first group and that is our second group. And here we have 2 options for the first set, either we're in it or we're not, and then 2 options for the second set, either we're in it or we're not, and we multiply that 2 by that 2 to demonstrate that we have 4 total options. So then I suppose it would make sense that when we have 3 different sets, we could have a vector that looks like this, maybe 1, 0, 1. Let's say that this is group 1, group 2, group 3. And so a vector that looks like this could represent being in group A, not being in group C, and then not being in group B, and then being in group C. And so that's this region right here. And if we have 2 options for A, either we're in the group or not, 2 for B and 2 for C, we multiply all those together, 2 times 2 times 2 does give us 8 different options of where we could be on this Venn diagram. And so here's where having this kind of general idea of what's going on is helpful, because if you just try drawing a 4 circle or 4 set Venn diagram, kind of using the same strategy as before, if you count up all the different regions, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This seems to break the pattern of these numbers on the right side, these powers of 2, right? We have 2, 4, 8. Shouldn't this be 16? And yes, it should be. It's just that this Venn diagram that I drew is missing 2 key spots. There's no place on this Venn diagram where we can have belonging to this group over here and that group over there without encountering anything from this group or this group. So this kind of quadruple Venn diagram must be drawn a different way. because we only have 14 different spots instead of the expected 16. So instead, I believe to draw this one, you're supposed to do like these kind of ovals that intersect slightly together here. And then I forget exactly how to do it. How about, let me just put an image right here, or I guess it'll be right here because it's mirrored. And then this is how you can draw a quadruple Venn diagram. And hopefully I'm putting an image there that has numbered sections so you can see that there are indeed 16 total. At least there's supposed to be 16 total when you do a quadruple Venn diagram. So this version right here actually is incomplete. Anyways, and yeah, the 16 comes from the fact that we have, two options for the first number, two for the second, two for the third, and then two for the fourth. Multiplying all those together, we get 16 total options, which, isn't the answer for today. I went too far. It's just this 8. This is our answer here, but I wanted to justify why it should be 8 in more than one way, 2 ways. So I think that's it. That's all I got. I'll see you tomorrow. Bye.